Thanks for coming. Thanks for the invitation. What I'm going to discuss here, there's basically two parts to it. One is an introduction to causal inference in a very general sense. So it's going to be highly simplified in the interest of time, but hopefully the ideas I describe here will be of use to everybody in the audience. So I'll try to describe some details of a particular piece of work of mine done with some collaborators. Let's see how much time I'll have to go into the details of that. I'd like to say beforehand that this is more of a methodological talk. I don't work on COVID directly, but I'll try to put in context these ideas that I have here on how they could be useful for COVID research and general practice in real applications. Okay. So I think before you start any enterprise, it's good to define its boundaries. What is this that you mean by when you talk about causal problems? So we have a system, maybe a natural system, a social, or could be even engineered system, and there's some change that happens to it. For example, via policy making or via novel prescription from a doctor. So there's some intervention that takes place, and when that takes place, you expect this to propagate somewhere into the system. So I'm not going to get too much in the philosophy, what is an intervention or not. Let's just assume you take for granted what an intervention is. Could be a change of interest rate, could be a new medicine that you prescribe to new people. Just take it for granted. There is such a notion that you can modify a system and see what happens. So this is particularly timely for what is seen now in terms of vaccination starting to take place. Of course, we don't believe vaccination is useful because it will cause changes in immunization rates. So what do you mean by cause in this situation? So I work mostly through hypothetical examples. So make use of some notation here. So we have some treatment X, for example, take a medication, and some outcome Y. Maybe this treatment is useless, which is not better than taking a sugar pill. But you can think of this maybe being a medication, the outcome being a particular measure of health outcome, like you get some disease or not in the next six months, for instance. Let's hypothetically say that the study that we have at hand is not a randomized control trial. Maybe somebody had an idea of using a particular off-the-shelf medicine like chloroquine, for example. You want to see whether this has any effect or not, but without doing a randomized trial. Under the assumption it's not going to cause any harm, so you might as well make this decision, make this judgment call that you should try it. So there will be people who get the treatment. You can say they have this value of X equals 1. And there are people who will escape getting sick. So Y being 1 is a good outcome. You don't get sick. Of course, you do people who don't get that treatment here. So let's say we observe the following result, that people have a higher probability of getting or not getting sick when they get this treatment. So I can describe this as since probability of not getting sick is higher on those who took the treatment. Now, you can see from the story that I outlined here, that is not necessarily the case that this treatment is good, right? I mean, it may be the case that by the physicians who actually look into prescribing them, they are not your regular physicians. They also take good care of their patients in other ways. So this may be actually the reason why those people do well. It may be people who choose to take medication and not particularly representative. There may be people who take good care of themselves in other ways. That's maybe the reason why they don't get sick. So this is a major problem when you don't have these controls on who takes treatment or not. And this is what is behind that usual saying that association is not causation, right? Here you do have an association. You see that X is associated with Y, but it's not enough to establish causation. You need somehow to understand when, how this variable was able to be generated. This variable X was able to be generated. So it's the difference between observation and intervention. That intervention will change the way this treatment was assigned. And you need to make some possible assumptions if you want to make use of data which didn't come from a randomized controlled trial. And you're going to see this is actually very common, even when you have past history of having some randomization being done. You'll need a mathematical way to describe what these assumptions are. So actually able to understand how the interactive data and what are the consequences of those assumptions. Okay, so in causal inference, you have this kind of combination of art, science, and mathematics to be able to draw these causal statements. It's an art and science because, well, you need to make assumptions. The assumptions will come from scientific knowledge, but they may not be too clear. They may be educated guesses. There may be something controversial about them. There will be some element of a personal decision here, not completely subjective, of course, but there will be some degree of expertise behind that might not be unanimous when you make these assumptions. But nevertheless, it's good to make them open and clear as much as possible. And that's where mathematics is useful, because it allows you to write this in a way that other people can verify where your conclusions come from. Now, the way this will play a role, the way mathematical modeling will play a role, is there'll be this, as I mentioned to you, ways of encoding assumptions and ways of calculating their consequences, which can be highly non-trivial. So as you may have seen from the title of my talk, there is some component to it, some computational component that may require some clever combination of mathematical principles and brute force algorithmic components to it. And because I come from this background of machine learning, AI, artificial intelligence, this is closely related to what people do on AI too, because you can think of encoding representations, encoding assumptions as a type of knowledge representation, very common enterprise in AI. And these algorithms for deduction also very commonly studied in computer science and AI. Okay, so that's where the interplay here will take place. And the way I'm going to represent that, at least in the context of this talk, and I want to say this is the only way of doing this, but it's becoming more and more mainstream ways of representing causal knowledge, is in terms of statements about independencies between random variables and intervention variables. So random variables, as you typically see in probabilistic modeling, statistics, describing quantities that you are getting from data that will be collected in random ways. Intervention variables that just represent your actions, whether they have a particular policy, whether you prescribe a particular medication. These will be your interventions. They can also be represented as variables, but not as random variables. They are actions that are set by design. And there'll be some interplay between them, these independencies. And that's where you'll be able to draw conclusions. So you need as input a convenient way of representing these independencies. And graphs are particularly nice for that. Under the hood, they just specify these dependencies and independencies. They are not the fundamental object. They are more like what programmers like to call a synthetic sugar. They basically display nicely these statements of independencies between random variables and intervention variables. So to be more concrete, let's use here a particular family of graphs, which are called direct acyclic graphs, or DAGs for short. And they're going to have vertices connecting random variables and these intervention variables, which are represented as vertices in these graphs. So we're going to use circles to denote random variables and squares to denote intervention variables. And it's possible to switch one mode to another. If you have data where people chose their treatment by themselves, self-selected, you can think this is a random process. So the treatment is a random variable in that case. And you can think of a controlled experiment where somebody sets the treatment by design. So that's not a random variable anymore, it's an intervention. So you can imagine this, you may have a same symbol switching its role from being random to be an intervention variable. You can represent that graphically. So in this talk, I'm going to mention this transformation using this notation from Udaper, which is a major influential figure in computer science, where he describes the so-called do operator. It's an operator that takes a random variable and sets that to a particular intervention level. And I'm going to make some drawings here for you, one of the reasons why I like to use my iPad, to make a bit more precise what I mean by statements such as X causes Y, okay? And maybe go into a bit of a more slightly more evolved example what I meant by the previous hypothetical case of a physician prescribing vaccination and affecting your health outcome. Okay, so let's say I'm going to represent vertices for treatment and for outcome like this. So this can represent a distribution of random variables, right? This DAG here is just one particular way of saying, oh, we have a model that generates random variable X. So this P of X here could be a probability distribution, could be a density function. The little p is just going to represent a model that generates these random assignments of treatments. And given that the random variables draw, I could imagine there is the next component of drawing my values. I could have the probability of generating Y given that X was generated. So this is a random process, just a joint distribution over two random variables here. That DAG just suggests one particular way of factorizing it. Now you can think that I'm doing an intervention X, so I'm doing an intervention that sets the treatment at a particular level by design. So this becomes my little x that is now a design variable, an intervention variable. And I still have y as a random outcome. So what I have here is a model for the outcome given a fixed value of x. Okay, there is no more p of x here because this was set by design. So the model now is just for one random variable y, and do x just indexes the regime by which this random variable is generated. So if you want to distinguish x causing y from y causing x, the joint distribution is not going to tell you much here, because this is just two different ways of factorizing the same joint distribution. But this would not be two different ways of representing the interventional distribution. Because what happens here is that now P of y given to x preserves the factor that generates y and erases the factor of x. Okay, so now it's still a random variable. Graphically, what you see is the edge between x and y disappear now. So in a situation like this, when x causes y, this variability of y depends on the levels of x. While here, when it's the opposite, the variability of y does not depend on the levels of x. This is independency that is asymmetric when you control x or you control y. And that's why causation is asymmetric according to this language, because you entail different independencies that are going to show up depending where I intervene. Okay, so if you think about the physician case, we have the choice of taking the medication as being X, the health outcome as being Y. Maybe you have the physician prescription being a common cause of X and Y. You may have some other sort of self-selection with socioeconomic status affects whether they take the treatment or not, and also affects how my health outcome by the end of the day. So it could be the case that there is no causal link between X and Y at all. This is what I mean by sugar pill. But X and Y is still associated because they have common causes. They are confounded. So this is called confounding. One way of trying to disentangle causation from association, therefore, is trying to stratify what happens in the different levels of PNS. So if I fix the levels of PNS, does the association between X and Y still remain or not? Or how weak or strong is it? This is what we call adjusting for possible confounders. This can be made also more precise to be able to link causal quantities of interest to the data that you have at hand. So if we have, for example, a randomized control trial, a RCT, one way of imagining that as a causal graph would be, I'm collecting data from this particular regime here. On the randomized control trial, if I was able to randomize, for example, whether somebody smokes or not, then the data generating regime would be this right-hand side graph that you see there, where the common causes, the possible confounding factors of smoking and cancer were overridden. There's no more connection between possible other causes of choosing to smoke and the actual event of smoking, because in this case here, I controlled it. So it became a square in my notation. There's no further connections into it. So it could be a randomized control trial where some people are made to smoke or not, to find a link between smoking and cancer. And that's why there was some controversy that Fisher didn't accept that smoking caused lung cancer because there was no randomized control trial. There was no randomized control trial because this is obviously completely unethical, right? You cannot tell people to smoke or not smoke. So all the evidence that we have essentially boils down to observational studies. That's how we learn that smoking is a major factor for lung cancers, not from randomized control trials. Okay. This comes from observation studies where the data generating process is like this. Smoking is a self-selected process. Would like to answer this question. The health outcome, how does it vary on the different controlled levels of the treatment, of do X in this case? We don't have data for that. We have data that may come from this distribution. This is called observation study precisely because you're just observing the treatment, not controlling it. Sometimes this is called coming from a natural regime. There's a natural way by which treatment is chosen. Sometimes an uncontrolled regime because you don't have this control on the treatment levels. But it boils down by the end of the day that all we have might be observational data, which might be of low quality. There are all sorts of other biases that may lurk into the data that you collected. But we'd like to answer the causal question on the left. We'd like to answer this question here. And somehow we have to jump from one type of data to one particular conclusion about a regime from which you do not have evidence directly. The issue that may happen is you may have some level of control, may have some level to be able to decide in a randomized control trial, like deciding whether some particular places you will throw a coin and say, I'm going to incentivize people from this particular postcode to take vaccination. From that other postcode, I'm not going to do any extra incentive. So this I could randomize. But this doesn't fully control the variable of interest, doesn't fully control vaccination, for example. So this wouldn't be answering directly the question on whether vaccination causes a particular health outcome because you're not completely overriding the contribution of possible confounding factors. And there are other issues. We may have a nice randomized controlled trial, but the sample that we have may come from very special people who may be particularly eager on contributing to our knowledge on something as major as the COVID effect. So the people that show up to a randomized controlled trial may or may not be representative of the population at large. So at large, you'd like to know the effect on a particular outcome over everybody, but your data might have particular biases because the volunteers might not be representative. Maybe for COVID, it's not a big issue because there's such a major impact that it across the board, we have volunteers from several different segments of society, but who knows, right? Maybe a different effect for different people, and you don't know what how subpopulations will capture in these studies. And finally, even if we have a nice randomized control trial and these treatments go in the wild, so to speak, they may have other effects that you didn't anticipate in your study. So maybe you had nice ways of deciding that the vaccinations were good for a particular health outcome of getting that disease or not, but for some other health outcomes. So does this have bad effect on pregnant women, for instance? Maybe you didn't control that at randomized trial time. So you're going to have observational data in the wild on whether particular side effects that you didn't anticipate will be causally linked to a particular treatment. So you still fall back in some type of observational data where you want to draw conclusions from. So because observational data will be there, even in the context where the randomized control trials essentially do need this causal inference for observation and perfectly controlled studies, the deductive and inductive components to it will be deriving consequences of assumptions, but of course inferring uncertainty on your estimates, because by the end of the day, all you have is data. So your data will be just estimates of particular features of the distribution. So there's this combination of uncertainty due to your assumptions and uncertainty due to the fact that all you have is samples from a particular process. Okay, so how do you do this deduction from assumptions into causal targets of interest? Well, one common way, which I hinted already in the physician example, was if I have a particular ways of intervening on X, I would like to block the effects of these common causes. So with graphs, you can read off particular independencies. I'm not going to walk through the details of that in the interest of time, but I could mention, for example, that even if you don't measure these common causes explicitly, you could measure some particular intermediate variables that block the influence of these common causes. So if you want to see what happens in the different levels of X, my intervention variable would not influence directly or indirectly how I get to change the distribution of Y. In other words, if it doesn't matter whether I'm collecting data under intervention or not, then I can use observational data to make conclusions about causal quantities. So in an example like this, for instance, if I block or if I condition, or if I stratify the relationship between X and Y in different levels of Z, if I just tell you the outcome of random variable X, then the fact whether this is an intervention or not will not matter. As I mentioned to you, the influence in this way will be blocked by X itself, so it doesn't matter what F is actually intervening on X or not. And the influence that might come from this so-called backdoor path, where if I tell you what X is, these two values might be associated. This influence will also be blocked if I stratify by some variables that are within these pathways from the confounding factors in X and Y. So you're blocking this direction and you're blocking in that direction too by using these possible variables in the back doors of, X and Y. So what does it boil down to in this case? So if you have a situation like this where the data comes from the left and your target is on the right, there are some usual laws of probability can always take as granted. There's just standard probabilistic statements. You can factorize distributions. You can make them conditional on a particular observation. But if you want is this intervention distribution, then you can look from this graph that this distribution doesn't change under intervention because you're breaking the link here. The link doesn't exist anymore. So when I intervene on X, I'm actually have my backdoor paths, my confounding factors coming from its natural distribution. In the original distribution, they'll be linked. The interventional distribution will be separated. So this outcome under intervention can be deduced by a formula like this. And this allows us to estimate different interventional distribution, because this expression that you see there does not depend on this do operation anymore. It disappeared. All you have on the right-hand side are statements about the joint distribution of X and Y and Z. And I could also answer causal outcomes under particular levels of Z2. I don't need to average over them. Okay, so for example, if you just want to know the expected outcome, the mean value of the outcome under intervention, as you have there, oops, sorry. Just want to know this. You could plug an estimate of the regression of Y on X and Z, and estimate of the distribution of Z. And this will give you an estimate of this causal response on an intervention of X using observational data. Okay, and there are many different ways of doing this. This is just an illustration that the same quantity can be inferred in different ways. So there's no single way of mapping this observation distribution to the causal question. But one of the questions that are keeping me awake at night, and many other researchers in causal inference, is, well, this assumed could block these confounding factors by stratifying over particular observed variables. But sometimes you can't observe these ways of blocking common causes. So one way of thinking about it is you may have some dependencies that are due to common causes, but here I may have some extra information like an imperfect experiment that even though it did not control X directly, may have ways of nudging the treatment level. So it's possible in some situations to identify the causal effect of a variable on another by using imperfect experiment. So there's some particular cases, for example, linear models, which I'm not going to describe in detail, but just hinting here. There are particular cases where imperfect experiment can still tell me what the causal effect of some X on Y is going to be. However, in general, you cannot do that. You have some nonlinear relationships, you cannot really do that. In the diagram that I'm showing here, you have, for example, discrete variables. You have some binary variables. You take or don't take the treatment, you get sick or you don't get sick. You nudge this person to take the treatment or not. So these are all binary variables, and there's no general linear relationship between them. So one way of understanding what you can do is to pretend there are some hidden variables that completely determine how you'd respond to a particular exposure. So what I'm showing this graph here is a relationship between choosing to take the treatment and being nudged to take the treatment. So Z here can be seen as a nudge. A physician or a public marketing campaign might make you want to take the treatment or not. So you may imagine that different types of people respond differently. So you may have people who doesn't matter whether they got nudged or not, they never take the treatment. You might have people who are compliers, they'll take the treatment if you tell them to take the treatment. You might have people who are always going to take the medicine, they don't care whether you nudge them or not. And there might be stubborn people who are defiers, they actually do the opposite of what you tell them. So you have 4 possible ways of responding to that nudge on the variable Z. So this may be interpreted as having some hidden variable taking 4 different levels, and you can play this game to other variables in your system too. Your outcome will have a similar structure. So you can think of all possible types of people that you see there. They're going to boil down to these 4 cases: this compliance, non-compliance, and so on. This is a problem that shows up a lot in medical stats because you may have treatments that cannot be controlled in a hospital. So you may send a patient home, and the patient at home may not comply with your treatment or not. So your treatment can be assigned in a hospital, but your compliance X may not be fully controlled. And you can imagine that different types of people who will never take or always take or just comply with you or do the opposite what you tell them to do, since you cannot fully control what they do. Okay. So in a situation like this, you don't have really ways of telling what the cause effect is, but you can get some lower bounds or upper bounds on the cause effect. Okay. In this case, it's still used for information. You can say that the response to this particular treatment is at least as strong as this, or at most as strong as that. So give this interval on where the cause effect might be. Now, the way this is achieved is that you can look at possible hidden variables. All those variables that I mentioned to you dictate how you respond. You can look at all these possible hidden variables that don't contradict what you actually see. So you'll see variations between Z and X1, Y that you can estimate from data. And these variations will impose constraints on how you can respond causally to treatments. So the game here is we're going to try to match the observable distribution, what you can possibly estimate from data, from distribution over these hidden variables that you don't see. And up to recently, it was very hard to do this when the treatment was continuous. If you wanted a dose response or access at a continuous treatment, you didn't have really a good solution for that until recently. So there works by econometricians, particularly Freud and Gonzalez, very recently, where they provided ways of understanding what you can do. In that case, the treatment variables are continuous instead of just a yes/no type of causal control. Okay, so one thing that I did recently, this was out just last week in this conference, Neuroinformation Processing Systems, was different classes of algorithms, these computationally components of these causal questions that will do the computation on how these bounds can be obtained. Okay, it does require some extra assumptions. Those response functions that I mentioned, the way you respond to treatments, they cannot be arbitrary. You need some sort of regularity assumptions on them, some sort of extra constraints on the shape they can take in the continuous case. But the assumptions can be very mild. And what I'm going to do in the next 5 minutes or so is to power walk through some of the ideas behind it, because I think to really grasp some of these ideas, I need to read something like our papers, but I wanted to show you the high-level ideas behind these problems where you can bound cause effects, even though you could not rule out the possibility of a hidden common cause confounding your treatment and your outcome. Okay, so the idea is there's a kind of inference engine. You provide information about the observable distribution. This information may have a statistical uncertainty. You can propagate it as part of your procedure. There's no elegant mathematical tractability. The way of approaching this computation of bounds on a cause effect, as you're going to see, will require some really brute force approaches for an optimization that will solve an optimization problem that gives the maximum cause effect and the minimum cause effect, which are compatible with the data that you see here. Okay, So one of the ideas is, so if we have the relationship between X and Y, you may have different responses on how different types of people that you don't see these different hidden common causes may take place. And if you fix this particular personal profile, if you fix this variable U or these hidden common causes affecting Y, then the way that Y responds to X will be a whole continuous curve, right? It can be a continuous curve like this, maybe a continuous curve like that, maybe U-shaped. There will be different possible ways that can potentially respond to treatment levels X. And each one of them may have particular probability. Maybe this curve has a particular probability of appearing, maybe that curve has a particular probability, maybe that curve has a different particular probability. So you need to define what these functions can possibly be. You need to define what this distribution can possibly be. So I'm going to work on this idea that there'll be a set of possible response curves and the distribution of these possible response curves that I want to be able to tell what they are, but I can try to play a worst case scenario type of game to see which ones of these don't contradict the data and which is the ones that can give me the largest and smallest effect here. So as I said in the previous example, these are your hidden causes, and you can imagine these hidden causes as clustering possible response types. So in this case, I'm only interested in the response of the outcome. There's different possible functions that I can put a probability distribution on them. So, I basically mentioned this already. In this case, for the particular work we did, we had functions of this type. We have some linear combinations of some basis functions. These basis functions files could be predefined, could be a wavelet basis, could be a Fourier basis, a polynomial, could be given by a pre-learned neural network. There are different ways of choosing these basis functions. What I don't know is the weight I'll give to each basis function. So this will be given a probability distribution. In the working example we had, it doesn't need to be that exactly, but we use multivariate Gaussian to describe these possible functions in terms of these coefficients. And this has parameters in itself. So if you're familiar with a Gaussian distribution, you need a mean, you need a covariance matrix. And this is what we don't know here. What would be this mean, this covariance of possible functions? So one way of tying them to data is saying, well, I want, for example, to find an upper bound on the causal response. Then I maximize over all possible distributions of functions, maximize over eta in this case. I need to maximize that to get an upper bound. I need to minimize that to get a lower bound. Can do that to different levels of X. So this will give me a whole dose response curve. And what I need to do here is to tie this to data. So I can have, for example, the data will tell you what the distribution of the outcome given this nudge variable Z would be. So they could estimate that from data. Yeah, I could tell that the model over these functions that I have here must agree on this observed distribution. Okay, this is one constraint I can impose. It must agree with the observable distribution, even though it comes from a hidden variable. So I just see the worst case scenario I can get in terms of maximizing what is distribution of eta. So there are some particularities here that in the interest of time, I just invite people here to look at these papers in more detail. There are some situations here where we want to actually look at something more simplified. So what I'm writing here is, instead of matching the entire distribution, you can match something simpler like the expected value of the outcome under different levels of the nudging variable needs to match what a causal model implies. So this would create a constraint on the distribution of possible hidden variables if it must satisfy this matching with the observable distribution. Okay, so it boils down to something that looks a bit ugly here. is a nonlinear programming problem that can maximize or minimize a causal effect in a way that it matches what I can possibly see. So the degrees of freedom there, therefore, it cannot pinpoint a cause effect. I can only get a whole range of possible cause effects here. So what do I get by the end of the day? There will be some issues there that I need to approximate what these integrals are. Again, I'm not going to get into detail on how to do this because I don't have time, but it's possible to avoid avoiding the need to calculate some of these integrals analytically. You can use Monte Carlo approximations to these integrals. This is heavily demanding on an algorithm, but it's doable. So when I do my optimization problem here of finding bounds, I'm actually evaluating these constraints by some randomized draws from simulator. So this is actually doable of today's types of algorithms. You don't need to rely on having any analytical shape for some of these causal effects. And what I'm displaying here is just one particular illustration using simulation studies. So I'm going to end on that note, that you may have, for example, observational data between some treatment X and some outcome Y, where the association is the reverse sign of the causation. Okay, so what I see in these dots that you see here, these gray dots you see there is a scatter plot. It's just a simple showing the observational relationship between X and Y. And it seems to be decreasing, right? It seems to have a negative association. The true cause effect is actually positive. So be badly misguided if you didn't take into account the hidden common causes between X and Y. So depending on the assumptions you're willing to make on the shape of these response functions, you can have, for example, assumptions that the associations, the causal relationship is linear and get bounds under this assumption that in this case, where the truth is indeed linear, will get you fairly informative bounds without assuming the presence or not of hidden common causes. If you assume a model more complex than what the truth is, you get a more conservative answer. So here the cause effect is linear, but I'm allowing quadratic functions in my cause effect. So I can get bounds which have the quadratic shape, which are overly conservative, but at least didn't make overly constrained assumptions. Okay, so this toolbox in one sense allows a scientist to encode assumptions about possible relationships that don't necessarily assume a way that you have measured the common causes. Okay, it will require these assumptions about the response functions, but they can be made as flexible as you want in principle. And of course, there's a trade-off. You get less information by allowing more flexible functions. You get tighter information on the bounds by using more constrained functions. Okay, so don't need to stick to pre-decided shapes of the response functions. This can be part of your study here. Okay, so this is basically summarized the relationship between scientific method in generating causal inference, because by the end of the day, it's a lot like what Feynman used to say in his lectures. It's about educated guesses and the computation of these consequences of the guess. And the way you need by the end of the day, of course, is to compare these results to what your data can possibly tell. All right. So thank you very much.
Thank you very much. That was very fascinating and very clear. So now's a great time to add your questions into the Q&A box. I see one person with their hand up. But if you want to ask a question, you need to pop it into the Q&A, I think, because the hand function doesn't work that way. So whilst we wait for a question to arise, can I ask, in the context of COVID or any other infection, it's naturally a difficult thing to work with, because whether you get infected is conditional on whether you were exposed in the first place, plus a whole bunch of other things. So can you say something about how that fits into the framework you've just described?
Yes. So I described a most simplified setup where exposures don't interact between different individuals. So in the case like smoking lung cancer, of course, we have secondhand smoking has have an effect. What one person does, one person receives, may affect other people too. This is what some people call interference. You can have treatments of an individual affecting other individuals too, or propagating to other individuals. This will require things like causal graphs that show relationships over different individuals. And this is another can of worms. It's definitely something which is within the realm of these models. There are models for interference, even based on social networks or spatial interference. There are all sorts of ways by which treatments can propagate across different subsets of people. I didn't mention this for the interest of making things simplified, but there's indeed a whole subfield of studying causal inference about interference problems.
Great, thank you. And yes, so there's still no questions appeared in the Q&A. So I will go on to my next thought, which was, have you any examples of where these continuous instruments might occur in?
Yes, so I skipped very brief here. I couldn't really talk about this example. So there's one example for econometrics where the exposure, so the treatment level is your total income, and the outcome level is how much of that you spend on food. So it's econometrics problem, and the treatment level, the instrument here is, my God, I forgot what would be in this case. Yeah, I think the instrument in this case would be, oh my God, then I drew a blank. Okay, the expenditure is the treatment and the salary is the instrument. So we have the salary of one particular individual in the household, and you have how much that person spends in general, and you have how much you spend in food. Okay, so this is the three different continuous variables being allocated here. I mean, of course, when you think about exposure, you may think about, for example, viral loads as being a continuous treatment. And you may think about a particular amount of time we spend in an environment as being the instrument. So yeah, this is one possibility. You can link different continuous variables.
Right, yes. So that's obviously a very relevant question as to, to what degree does it matter how long you spend around infected people if you're, because the NHS app has this magic 15-minute cutoff, where if you're below 15 minutes, then you're totally fine, and then it switches to you're probably infected. And of course, the binary response is wrong. And so what you're saying is that you'd be able to use contact time if that were recorded in the app, and you'd be able to use that contact time as an instrument for the ongoing outcome.
Yes, I mean, there are other issues on instruments that you may want to take into consideration. That they will require domain knowledge about this. But in terms of the plausibility of continuous instruments, I think this is actually fairly common to have continuous instruments. But the main challenge here is actually the continuous treatment, the treatment being a whole dose response.
I see, yes, I think that's right. So I think we might circle back to this in the panel session because I feel like it's relevant in interventions on economies. Thank you very much for that really fascinating talk, and it's a virtual round of applause. That because we disabled the round of applause button, it's in fact silence, so I'm sorry about that. But thank you very much.
I'll see you soon at the panel.